Hey, welcome to the 8th video in this series on deep learning in MATLAB. So this video will be slightly different where I'm not going to create any new network because I've already done that a bunch of times. What I will do is introduce you to some features of MATLAB um, that are data stores and some optimizers. So let's first begin with data stores. So the way deep learning works in real life is you typically have lots and lots of data. Like the size of your data is less than the size of your memory or your RAM. So there's no possible way where you can load in your data. For small example, it works. You can typically load MNIST entirely in your memory, or some small examples, you can always load them up into your memory. But when you're doing some large data analysis, it's impossible. So the way deep learning networks deal with this issue is that data is never loaded into memory. Data is stored wherever it's stored in the hard disk, and MATLAB, so rather, or any other framework for that matter, reads in only a batch worth of images or data at a given time. So MATLAB or any other third-party framework, what it would do, it would read a batch worth of images into the memory, do the training on it, and then load the next batch. So that way, you're never exceeding the capacity of your memory. Okay, so the way MATLAB handles this thing is by using data stores. So, for example, the MNIST dataset was a bunch of files. So here, let me pull that up. So if you go to MATLAB's folder and then you navigate to this directory, nnnet, nndemos, nndataset, you will find this folder containing 0 to 9. So let me go into that and you will see. So for example, if I entered the folder 4, you would see all the images of 4s. So that's um, lots of images, right? So each image is represents 4 and it's a PNG file and it's different. Now, what here they have done is there are like 10 folders and the folder names are the labels. So this is what you typically do. So for image classification, this is a norm where you create folders where the folder names are the labels of what they signify. Here they are the digits. So digit 0 contains all the images of 0. Digit 1 contains, or rather folder 1 contains all the images with digit 1 and so on. So this is my directory that contains all the images. Now when I create a data store out of it, what the data store does, it just lists down the file names for all the files in each folder. So that's all it does. It just like takes, just registers all the file names. And when you read in data, or when you read in a mini batch, it will load in the corresponding files. Okay, if that makes sense. So data store is just um, let's say it just reads in all the file names in from your data set, and then when you read the data store, it loads the files corresponding to those file names into memory. So we will see an example of this for MNIST, and I will go over that. MATLAB supports quite a few kinds of data stores where you can deal with different kinds of objects. So for images, there is image data store. For spreadsheets, there's that. For tabular data, there's that, and yada yada yada. We only care about image data store, so let's check that out. Great. So here's the documentation page for image data store. And the way it works is all you have to do is specify the location, or rather the folder that your where your images are. And it is advisable to put your labels as folder names and put all your images belonging to that label inside that subfolder. All right, so let's try to read in MNIST. Okay, so I have already created a live script and you can find it in my GitHub page, which the link for that you can find in the description below. So first of all, so I'm going to load in the data. So let me get it here. Great. So first I define the location. and I put in the location of that folder. And then I create this image data store object where I pass in the file location and I tell it to include the subfolder. So if I don't pass this flag, it won't read the images contained in the subfolders and hence it won't read any images. And then there's an additional option where I specify that the label source is the folder names. So this tells or rather this tells the data store object or the image data store that the labels are the folder names itself. All right, so let me run this. So when I run it, um, you see it loaded in a bunch of files. Actually, let me pull up MATLAB. Might be more useful looking at it from there. Let me clear up all the old variables and let me run this again. Great. So here it created this IMDS object, which is an image data store. When I double click on it, um, we can see the data associated to it. So if I go to files, as I said, this contains all the file names and their paths in our data set. And the folder contains which folder it's found in. And then the labels are basically the labels of each image. So this corresponds to the file names and files. And the labels were read from the folder itself. So there's 0 to 9. Great. Right, and then there are like some other supporting functions. Now, this is an interesting object called or property read size. So that tells you how much or how many images do you want to read at a time. So this is what we typically call the mini batch. So how many images you want to get at one instance. So if so right now the default value is 1. So when I type in read, it'll output 1 image. So let's first see that. So if I go back, um, and to read from a data store, all you have to do is just type in the read command. Pretty simple, read, and then pass in the data store. But then I want to show you what it reads. So okay, let's first have a blank output. So on the right, you can see it read a 28 by 28 image. Now if I do imshow, you see it read a 0. Now the thing with read is read always reads the data sequentially. So once I type in the read command, it read the first image. Now when I type the read command again, it'll read the second image. It won't read the first image. So it does things sequentially till it reaches the end of my data store. Now you can always shuffle your data store around to shuffle the values and then do the read. But read, again, always works sequentially. So you can't reread a file, if that makes sense. Well, you can do it, but not in a straightforward manner. Great. Now let me change this property of read size to be, say, 5 images. I want 5 images to be read. Okay. Um, Sorry, I made some error. Yeah, 5. My bad. Okay. So now let's try to read in the images. What's the output? Oh, because I'm reading 5 images, I need 5 variables. So A, B, C, D, E. Huh. Let me debug this. It turns out this, so if I go back to this data store variable, it was never updated. So the read size was never updated, so it was still at 1. Let's change it to 5 and let's save it. Sorry. Um, let's see if it's 5 and let me just double check if the change was permanent. Okay, yeah. Oh, great. Now let me go back to my notebook. Right, so now when I do read, um, Oh, my bad. I see. So every time, so when I execute this, this also gets executed. So it resets the value of the read size. So I should probably specify the read size as a property. So what I can do is here, I can specify dot read size as 5. Great. Okay, now let's read. So here, so once I read this data store, you can see I got 5 images. So that's how you read a mini batch of data at a time. So this is what we saw in this MNIST example in the beginning. In the MNIST example where we created, which we created using some layers. So the first few lines of that example were creating this data store. So now if you go back to that video, you will have an idea about what a data store has, or you will understand those 2 lines better. So this is pretty much it about data stores. You can again read much more about them in the documentation page, and I really don't want to go over the details of a data store of all things. So again, here's the link for the documentation, and pretty easy to use. The next topic I want to cover is gradient descent. So in the in the network that we built, so we built networks 3 ways, using layers, using from scratch, using DL arrays, and then we also used the deep network designer. So when we created the network from scratch, we were training it using gradient descent. So if you remember, gradient descent was something like this, where your parameters updated according to the gradients of the according to their gradient with respect to the loss function. So here is the parameter in the next step, which is the old parameter minus a learning rate, which is called alpha, times the gradient. So that's what we had used, which is the most basic way to train a network. So this is the gradient descent algorithm, and it's the most basic way to teach an algorithm. Now, MATLAB provides you some sophisticated solvers for optimizing or training your networks. And let me point them out. So, oh, let's see. So, one of them is SGDM, which is stochastic gradient descent with momentum. And then there are like 2 more. So, there is so these are, so what page am I in? I am in training options. So, this is basically what are the options that you have for training a neural network. And if I go down to the algorithms, you'll find that I have stochastic gradient descent with momentum, I have RMS prop, and I have Adam. And this page also lists down the theory behind each of them and how they work. This was our basic gradient descent that we used in the example where we created this, where we trained the network from scratch. Um, Also, if you remember when we used the deep network designer in the last step where we were training the network, we had to pick the algorithm that we wanted to use. And we had picked SGDM, which was precisely this. And if you go back, you would see the other 2 options as well. Now, these 3 are more or less pretty performant, equally performant, I would say. But these are more sophisticated compared to the regular gradient descent. And again, you can read all about their theory here. But I just want to give you a flavor on how one would go about using these algorithms in their network. Now, the way stochastic gradient descent with momentum works is that in addition to this gradient descent step, as you can see in this equation, there is one additional term. So what this additional term does, it keeps track of what were the gradients. It has a memory of what were the gradients in the previous step. So in a way, it's like having a momentum. So imagine you are driving and you keep on driving straight. So you have some velocity associated with your in your car, and you have some momentum. So if you have to stop immediately, um, it takes a lot of energy to slow down and to stop because you have a lot of momentum associated to it, to your car or to yourself or whatever. So in the same way, in a stochastic gradient descent with momentum algorithm, wow, that's a lot of words. But in SGDM, when the network sees gradient gradients in the same direction, it learns quickly in that direction. And if it sees some gradient in the opposite or some tangential direction, it won't move in that direction immediately. It will first slow down in the direction where it was going and then start to move. So there is a momentum aspect to this gradient descent in the same way as physics. More mathematically, this algorithm just keeps a track of your weighted average. I think it's exponentially weighted average, but again, like I don't remember, but a weighted average of your previous gradients. So that's why if you see the gradients here, there's a difference of gradients between step L and step L minus one. So gamma here is a new hyperparameter that has been introduced, which is called momentum. Okay, so let's see how you implement this in practice. So let's see what are the hyperparameters. So the first one is alpha, which is the learning rate. Gamma is the momentum hyperparameter. And then this quantity is also something that we need to keep track of because this is the difference between gradient in current step and previous step, right? So this term in literature is called velocity, and that is something the algorithm will automatically keep track of. So I'm going to show you how to implement a very simple version of this algorithm. And the command for this is sgdm update. Pretty straightforward. So let's see how to apply this in action. All right. Um, let's see, how do I... Okay. All right. So I have defined my parameters here. Suppose I just have three parameters, 0, 0, 0, and I have some gradients, 1, 1, 1. Now, in the first step, so again, remember, velocity is this difference between gradients in current step and previous step. But in the first step, there is no previous step, so it starts off empty. I define a learning rate of 0.1, a momentum of 0.95, and all I need to do is pass in SGDM update, the parameters, the gradient, the velocity, the learning rate, and the momentum. Lots of things. And it gives two outputs, the new parameters, which you need, and you also need this velocity because you also need to keep track of this difference for the next step. All right, so before I press, so before I, let's see, so let me put a section break here. Okay, so here I define the parameters and let me run that. Great. So what should be the result, right? So in my first step, my parameters are 0 minus 0.1 times the gradients. So the gradients are 1, 1, 1. So it would be minus 0.1. And then since the velocity is 0, this term is also 0. So my parameters would become minus 0.1. So let's see. So when I run this, you can see my parameters are minus, you probably can't see. So let me just move my video over here. So you can see minus 1, minus 1, minus 1. Right. In the next, so if I run it again, what would happen is now the current gradients are minus 1, minus 1, minus 0.1, minus 0.1, minus 0.1. And then I have minus 0.1 times the same value of gradients because I'm not changing the gradients. And so let's do a quick ballpark calculation. I'm just doing this in detail so that like you get an idea of like what's going on. Okay, so okay. So it's 0.1 and I'm just taking one element as an example. This is the learning rate times the gradient. Sorry, the gradient is 1 plus what's my momentum? So 0.95 times this difference. Now this difference is the velocity parameter, and let's see what is its value. So if I go back, to MATLAB's variable editor, the velocities are negative 0.1, negative 0.1. Okay, because that is the difference between 0, 0, 0 and one step that we have taken. So 0, so it's negative 0.1. All right, so this becomes 0.1 minus 0.1 minus 0.095. Uh, let's see. Oh, this is also a negative. So I should get 0.295, right? This makes sense. I hope I can do the math right. All right, so if I run this step again, I get 0.295. Okay, great. So here in this method of doing stochastic gradient descent, MATLAB takes care of all the math regarding this step, so we don't have to manually update, and you can just loop this step over n number of times. And again, if you look at the documentation page, you would see more sophisticated ways of tackling gradient descent. So yeah, so that's pretty much it for this video. We discussed data stores and we discussed these gradient descent algorithms. Now these two are like they're not part of the network architecture, but these things are important in how do you train your network, because creating a network is only 10% of the job. Like optimizing the training process and optimizing your network and getting the data in the right form and all that would take most of your time. So these two things are pretty important. All right, so that's it for this video. I hope you guys have a good one.